Okay, let's start with today's lecture. Let me first briefly recap what we did last time. So in our last lecture, we discussed the von Neumann entropy. In particular, given the von Neumann entropy, we also defined other quantum entropies, such as the joint entropy, the conditional entropy, and the mutual information between two quantum states. Right? So we had that the joint entropy of a composite system A and B, so SAB, was simply the von Neumann entropy of row AB, so of their common state. So it's minus trace row AB and then the logarithm of row AB. And then we get the conditional entropy, so row of A conditioned on B was the joint entropy minus the entropy of B. So it was defined similar as in the case of classical random variables. And then also we defined the mutual information of A and B, also similar as in the classical case, namely as the entropy of A plus the entropy of B minus their joint entropy. And then we also discussed some properties of the von Neumann entropy. For example, that it's increasing under projective measurements, or we discussed the subadditivity, which was that S of AB, so the joint entropy, is smaller or equal to entropy of A plus entropy of B, right? And then we also discussed the concavity of the entropy and the entropy of a mixture, so which was as follows: that some x with some probabilities px, S of rho x smaller or equal to the entropy of this state given by the ensemble px rho x smaller or equal to to the Shane entropy of this probability distribution plus sum over x px S of rho x. Okay, we didn't prove these two inequalities, and we are not doing it now because of reasons of time. I mean, this proof it's not very simple, but it's not too hard. It's written in the manuscript. So if you're interested in the proof, take a look at the manuscript. Okay, we're now continuing with some more properties of the von Neumann entropy. Some of which we prove, some of which we don't. And we start with a very important property, the so-called strong subadditivity. So it's theorem 3.20. The strong subadditivity. As follows. So for a composite quantum system, A, B, C, we have that the joint entropy S of A, B, and C is smaller or equal to, plus S of B is smaller or equal to S of A and B, so the joint entropy of A and B plus the joint entropy of B and C. So the proof, so we're not doing the proof here, it can be found in the literature, for example, in the book from Nielsen and Huang. So see, for example, page 501 in Nielsen and Juan. The reason that we are not showing it because it's fairly complicated. By this I mean that we need some more other properties in order to be able to prove this. So some things which we didn't prove so far, or which we didn't show so far. So we're gonna take this as it is and we don't prove it. But it's a very important property. The reason is that, as we will see in a second, some other properties directly follow from strong subadditivity. And let me also state that the reason why we're stating all these properties has an aim, right? The aim of today's lecture is that we want to prove the so-called Holevo bound. Okay, what it is, we're going to see in a few minutes what the Holevo bound is. And for this, we need some tools, and those are the tools, so those are the properties, right? Because once we know these properties of the entropy, we can use it in order to apply it to some interesting sceneries. And right now we are still at the stage of figuring out what properties we have. And after we're finished, we can then take a look at the specific scenery, which again will involve Alice and Bob. And then we will see what the Holevo bound is, and then we will use these properties that we're going to show now in order to prove this bound. So as I said, this strong subadditivity is important because it directly leads to other important properties, and one of them is the so-called is the next theorem, which is called conditioning reduces the entropy. Okay, it's theorem 3.21. Let me first state the theorem, and let me then say a few words. So it's as follows: for a composite quantum system, A, B, C, we have that the conditional entropy S A conditioned on the system BC is smaller or equal to the entropy of A conditioned on B. And what this, I mean, just as the name of the theorem tells us, it tells us that if we condition, so conditioning reduces the entropy, meaning that instead of conditioning only on B, if you condition on both B and C, then we get a reduced entropy. Okay? It is intuitively kind of clear that we must get a reduced entropy if we compare this with the classical counterparts. Right? If I take a look at this, what is it? It's the information that we can get about system A. So if we measure system A, conditioned on the fact that we got already system B, right? And if we have more information available, then this can only lead to the fact that we have possibly more information about our system A available, right? So if instead of knowing system B, we also know some system C, then we possibly get some more information about system A, such that this must be smaller here on the left-hand side. Because once we know B and C, it then appears that we possibly have got already got some more information about A, meaning that this entropy here must be smaller. Okay, this is how you can imagine this by connecting it to the classical counterpart. But we've already seen that this analogy doesn't hold all the time, right? Between the Schoen entropy and the von Neumann entropy. So be careful with drawing this analogy. Okay? Here you can do this, but it's not. You can do this all the time. So let's now prove this theorem. So proof is as follows. what we do is we use the definition of the conditional entropy. I just wrote it down here. So we use now this definition using the definition of the conditional entropy. We get the following. So for the left-hand side, we have that joint entropy of A, B, and C minus the joint entropy of B and C is smaller or equal than the right-hand side is the joint entropy of A and B minus the entropy of B. Okay, so let's rearrange this a bit. Is the joint entropy of A, B, C plus the joint entropy of B smaller or equal to joint entropy of A and B plus the joint entropy of B and C. Well, and what is it? It's simply strong subadditivity, right? If you compare this with equation 158, so by comparing with 3.158, we see that this is the strong subadditivity. Well, and this finished the proof, right? Because given that strong subadditivity holds, we can go the other direction because there's an if and only if condition. So from this strong subadditivity then follows this conditioning reduces the entropy, right? And you see that those two theorems are kind of equivalent because from this it directly follows that we have, so from strong subadditivity it directly follows that conditioning reduces the entropy. Okay, so then there's another property which directly follows from strong subadditivity, and this is our next theorem, namely it tells us what happens if we discard a quantum system. So what happens to the mutual information if we discard a quantum system? So it's theorem 3.22. Called discarding quantum systems never increases the mutual information. So again, for a composite quantum system, A, B, C, we have the following, that the mutual information of A and B is smaller or equal to the mutual information of A and the composite system B and C. So as the name of this theorem says, if you take a look at the mutual information, and instead of considering the mutual information between the system A and a large system B and C, if you now discard one of these, say C, then the mutual information must decrease. Okay. You possibly remember that the mutual information Do we have it here? We proved it at some point. I'm gonna add it here for a second. So we proved at some point that, did we prove it? I think, let me take a look. Since we didn't, no, we didn't, sorry. Okay. Okay, no. No. So what we see here, so how you can see this, well, if you remove one system, then mutual information must be smaller. The reason is that, for example, if you take, say, this system C is very big, and system A is also very big, and system B is very small, okay, then this mutual information cannot be great, or is kind of restricted on how much information I have about system B. In the sense of, okay, I mean, that's how it is. I think I cannot say much more to this. And instead, we're going to prove it. And as I told you, it directly follows from subadditivity. So what we do for the proof is we can use the definition of the mutual information, which we also stated here at the recap. So using the definition of the mutual information, we have the following. So we can rewrite this equation 161 as follows, namely as the entropy of A plus the entropy of B minus their joint entropy, smaller or equal to the entropy of A plus the entropy of BC minus the joint entropy of A, B, and C. Right? Here we see that the entropy of A cancels. Now, rewriting this, we get the entropy of A, B, and C plus the entropy of B, smaller or equal to the entropy of A and B plus entropy of B and C. And this again is strong subadditivity. And given that strong subadditivity holds, we proved this theorem, right? Now there's one more property that I'd like to state. So the next thing that we consider is what happens to the mutual information if we perform a trace-preserving quantum operation to one of these systems. Okay? So consider the mutual information between system A and system B. And then the following theorem says that if I perform a trace-preserving quantum operation on one of these systems, then this can only decrease the mutual information. Okay, so performing trace-preserving quantum operation must decrease the mutual information. This is theorem 323. Quantum operations never increase mutual information. So for this, let AB be a composite quantum system. And let E be a trace-preserving quantum operation. And say that it acts on the subsystem B. And say that S of AB is the mutual information before we perform this trace-preserving quantum operation. So let SAB be the mutual information between A and B before the operation. And S of A prime, B prime, it's now the mutual information after we perform this quantum operation. So this we indicate by this prime. After E was applied to subsystem B. Then the mutual information after this quantum operation is smaller or equal to the mutual information before we applied this trace-preserving quantum operation. Okay, and we're going to also prove this theorem. In order to prove it, we introduce now a third subsystem, which is the subsystem C. So let C be, let's introduce subsystem C, which is initially in a pure state and uncorrelated with B. Such that this trace-preserving quantum operation on B acts as a unitary on this composite system B and C. Okay, so we enlarge, say, the system B to a larger system, such that this trace-preserving quantum operation can now be modeled by a unitary operation on this composite system B and C. Right? This is what we also know from our studies on quantum operations, that this is possible. So, such that E acts as a unitary transformation on the composite system BC. So now we use the fact that C is initially in a pure state and is initially uncorrelated to B. Okay, and since this is the case, so since B is initially in the pure state, and since C is initially in the pure state and uncorrelated to B, we have that the mutual information of A and B initially is equal to the mutual information of A and B and C. Okay, so we simply took C such that it's uncorrelated, and by the fact that it's uncorrelated and that it's pure, you know that the von Neumann entropy of pure states is 0, right? And this, by these two facts, we can say that the mutual information between A and B is equal to the mutual information between A and B, C, okay, because this system B doesn't matter. Right, and the next thing we use is that this unitary transformation, this trace-preserving quantum operation on system B acts as a unitary transformation on system BC, meaning that it does not change the mutual information between the system A and the composite system BC. Okay, because if we apply only unitary transformation on these subsystems, this does not change the mutual information. Okay, so, and since this map E acts unitarily on BC, we have that S of A B C is equal to S of A prime B prime, the composite B prime C prime. Okay. So, and what we're going to do next is we have to discard one of these systems. And this is what we just considered here. What happens if we discard a system? Well, if we discard, then the mutual information must decrease. Okay. So we use this fact now. So using, what is it, 168. We further have that S of A prime B prime C prime, S of A prime and B prime. Okay? We simply applied now this theorem. And now we can put all these things together, right? If SAB equal to this one equal to that one, and this one is greater or equal to this one. So altogether, we found that S of A, B is greater or equal to S of A prime and B prime, which proves our theorem, right? So these are all the properties about the von Neumann entropy that I wanted to discuss. And given these properties, we can now continue and try to put this a little bit more into a context, right? And what we're going to do is we come back to our communication protocol between Alice and Bob that we considered every now and then. Our next section is the so-called Holevo bound, section 3.3.6. Okay, as I just said, let's take a look at this communication protocol between Alice and Bob. So suppose we have here Alice who communicates with Bob, and suppose that Alice prepares some states, so some quantum states, rho 1 to rho n, with probabilities p1 to pn. Okay, so we can, given that she prepares these states with these probabilities, we can associate now this probability distribution that she uses, can associate it with a random variable x, right? So you can imagine as Alice having this random variable, and then she draws one item from this random variable and sends it to Bob, right? And Bob knows that she's drawing from this ensemble with these probabilities. Or, right? So what he gets is the state rho is equal to sum over x px rho x. Well, and his task is to figure out what the outcome was of this random variable. So which state did he get? That's his task, right? And this is the scenery that we considered so far all the time, or very often. It was very often we motivated our studies by this case, and we've seen that if these quantum states are mutually orthogonal, well then Bob can perform a measurement such that he can perfectly discriminate the states, and by this fact he can learn the outcome of this random variable with certainty, right? But we've seen that once these quantum states are not orthogonal anymore but mutually overlap, then Bob cannot discriminate them with certainty, right? And this motivated then our study of these information quantifiers. However, what we didn't do so far is we didn't take into account that Bob must perform a measurement, right? And this now what we add to the scenery. We say now, okay, Bob performs a measurement of the state, and we ask, given the outcome of this measurement, how good can he learn what the random variable, what the outcome of the random variable was? Okay, so suppose now Bob performs a measurement, and we describe this measurement by a POVM. So suppose he performs a POVM with measurement elements, say EY. Okay, and then he gets the probability for the outcome Y. Let's call this, okay. I write it in this way or in this way. And what this is the trace of EY rho. Okay, because rho is the state that he gets, and these are the measurement operators, and this gives us then the probability that he gets the outcome corresponding to this measurement operator y. Okay? So in the end, if he performs this measurement, what Bob gets, so what he's dealing with, is a probability distribution py. Okay? And this probability distribution we can now associate with a random variable y. Okay? And now, given this random variable y, how much does Bob learn about the random variable x? Well, if we think about it, what we find is that the information that Bob learns about x must be given by the mutual information of these two random variables. Okay? So Bob learns h of, so the mutual information of h, x, y bits of information. About the random variable x. Right. So let me write this down in a full sentence. So the amount of information gained by Bob can be quantified by the mutual information h of xy of the random variable x, which Bob would like to learn. And Bob's measurement outcome y. Okay, now let's take a look at the case, at the extreme cases. So we know that, so let me briefly recall, from some theorem, it was theorem 314, we know that the mutual information h of x and y must be smaller or equal to h of x. Okay? Meaning that Bob learns all the information about this random variable x if the equality holds. Okay? And we also learned that the equality holds if and only if those quantum states are mutually orthogonal. Okay? So from this, we see that if and only if we have mutually orthogonal quantum states, Bob can learn all the information about this random variable x. So once we are dealing with quantum states which partially overlap, we cannot learn all the information about this random variable. So Bob can infer this random variable x with certainty if and only if this mutual information is equal to the Shannon entropy of x, So this was theorem 3.14. So meaning that this means, or okay, the closer h of, so the closer the mutual information to this chain entropy of X, the more information has Bob about X. And this means that, okay, what strategy does Bob do? Well, he tries to choose his pure VM such that this mutual information gets as great as possible, right? He wants to maximize this mutual information because he wants to learn as much information about this random variable X as possible, right? And this, this maximum of information is the so-called accessible information, okay? We define this now, Bob's accessible information, as the maximum of the mutual information with the maximization over all possible PUVMs. So this is definition 3.16. Namely the accessible information of an ensemble given by probabilities px and states rho x. Let me call this ensemble E, associated with the random variable x. Is defined as follows. So we write this as the accessible information of this ensemble given by a maximization over all PUVMs, and we maximize over the mutual information of this random variable x and the random variable associated to the measurement outcome. So with the maximization, over all PUVMs E1 to EM. Well, let's state this differently. All PUVMs EY with outcome Y. So by outcome Y, I mean the probability distribution of this outcome, which we can associate with this random variable Y. Okay. Okay, so I think it's clear. And I mean, this now we motivated this by this communication protocol between Else and Bob. So I think it's clear what it says. It tells us that if Bob is given this ensemble E, then the right-hand side tells me how much information can Bob infer about this random variable X at most, given any possible measurement that he can do, right? So we maximize over any possible measurement. And from this, you directly see that, well, calculating this right-hand side is in general not easy, right? Because you would have to take every possible measurement into account. And for such expressions, it's often not easy to find a suitable solution. And however, what we can find is an upper bound of this right-hand, so of this accessible information. And once we have an upper bound, we at least know that our accessible information must be smaller than this upper bound, right? And the upper bound of this accessible information is the so-called Holevo bound. So let me now state the theorem of the Holevo bound, and we're then going to prove it after the break. So theorem 3.24. It says that for an ensemble, say E again, it's given by these probabilities Px and density operators rho x, with associated state, rho given by the sum over these probabilities and states. So this is the state that Bob would receive in this communication protocol. The accessible information is bounded by as following. So the accessible information is smaller or equal to the von Neumann entropy of rho minus sum over x px and the von Neumann entropies of rho x. Okay, so this is what it now tells us, is that at least we know an upper bound of this accessible information. Okay? So even though for most cases in general we cannot do this maximization, or it's really hard to do this maximization over all POVMs, at least we know an upper bound. Okay? Well, it can happen that this saturates, right? Because it's small or equal, but it's not necessarily true that this upper bound saturates. And in the exercises, you will do an example where this Holevo bound is not so there's no equality. So you will calculate both things. You will see you will be given the maximum of this Shannon entropy, so the maximum mutual information, and you will calculate this Holevo bound, and you will see that this is greater than the optimal solution, right? And we're going to do a break now, and after the break we prove the Holevo bound. Okay, let's continue. Before the break we just stated the Holevo bound theorem. Let me briefly recall this, and then we're going to prove it. So what we've seen before is that the accessible information of an ensemble was defined as a maximization over all POVMs, and the maximization is over the mutual information of the random variable x which is associated with the ensemble, and the random variable y, which is associated with the measurement outcome. And with the Holevo, the theorem of the Holevo bound then says that this is bounded from above by the von Neumann entropy of rho minus sum over x px, and then von Neumann entropy of rho x. Okay, so I'm going to prove now this bound here. And in order to do that, let us now consider a tripartite system. So a tripartite system P, Q, and M, where the system P we call the preparation system. So it's a preparation system with the following ON bases, with ON basis X, which label the states, and then we have subsystem Q is our quantum system, and in this quantum system those states rho x, they live in this quantum system. This is the system which Alice sends to Bob. And then the subsystem B, M, and subsystem M. This is the measuring device. And it's such that the orthonormal basis states so we call them Y, they correspond to the measurement outcomes. This means that if our measurement device is in some state Y, then it says that the outcome of the measurement was Y. Okay. And next we model now, first we consider, okay, how does the state of this tripartite system look before Bob performs the measurement? So before Bob's measurement, we consider this following state. So we have rho P Q M equal to sum over x px, and in the state x, our quantum system state rho x, and the measurement device is in some state 0, which is the initial state. Okay, and you see now this is the system P, which was our preparation system, and it labels those states rho x. So recall that those x here, this cat x, are also orthonormal, right? And they label those states of our quantum system. And then we have the measurement device, which is initially in 0. And next thing we're gonna see is how do we model now this measurement performed by Bob. So Bob's measurement according to the following P over M of the POVM is modeled by the following quantum operation. So by the quantum operation E acting on the system Q and M, but not on P. So we have the operation acting now on this subsystem of Q and M. So on rho x tensor 0, 0 is given by the sum over y, and then we have square root of ey rho x square root ey, then tensor y y. So this is so what this does, so this is the quantum operation with which we model this measurement, and what it does is it measures according to this measurement operator Cy, and what happens is that the measurement device, so this system M was the measurement device, and it tells us then, okay, the outcome is Y, so it is in this state Y, with the states being orthogonal. Okay, and the first thing we note is that this is a trace-preserving quantum operation. The reason that we show that this is a trace-preserving quantum operation is because we can then use the theorem that we just proved about how the mutual information behaves under trace-preserving quantum operations, right? So first note that this is a trace-preserving quantum operation. So we can calculate this, the trace of this, so which is sum over y ey rho x square root ey tensor y. Okay. So this is then the trace. So if we first trace out this measurement device, this is easy, right? Then we have here sum over y square root ey rho square root ey. And next we use the cyclic property of the trace. So this is equal to trace of sum over y ey rho. And then we know that these measurement operators sum to the identity, which is the completeness relation. So we are left with the trace of rho x. Sorry, this must be rho x. And since rho x is a density operator, this gives simply 1. Okay, so we see that it's a trace-preserving quantum operation. Let us now state the state after the measurement. So and the state after the measurement we get if we act with this quantum operation on our initial state. Okay, so we then get the state that we call this then P prime, Q prime, and M prime, which is the state after the measurement. Okay, so it's then a sum over x and y, and here we get then so our preparation system remains in state X, right? And then our quantum system changes to EY rho X and then again square root EY, and the measurement device is in Y. Okay. So what we're going to do next is we take a look at some usual informations. So first, so what's important now is that we have the state after the measurement and the state before the measurement, right? And we start now with considering the mutual information between the subsystem P and Q before the measurement. So, and before the measurement, we have that the mutual information between P and Q is equal to the mutual information between QP and Q and M, because this subsystem M is uncorrelated to P and uncorrelated to Q. Okay, so we can write it in this form. So next, we use that the measurement operation is trace preserving. By the theorem, which we stated before the break, which was theorem 3.23. We get the following, meaning that this mutual information S of P and Qm, this one cannot increase, okay, under trace preserving quantum operations. So here we simply applied the theorem. We said that the mutual information after the measurement of this subsystem Q must be smaller than before. So, and what we do is now finally we discard the subsystem Q. Okay? This leads to S of P prime and Q prime M prime is greater or equal to S of P prime M prime by theorem 3.22. So we used that discarding quantum systems can never increase the mutual information. And now we can put all of this together. So it gives S of P prime M prime, which we have here. So it's smaller or equal to this, this again is smaller or equal to that, and this one is equal to S of PQ. Okay, so we have S of P prime M prime smaller or equal to S of P and Q. Well, and this is already the Holevo bound. And to see this, we're going to have to do some rewriting. Okay? We're going to now rewrite both sides, and we will see that the left side is the left-hand side of the Holevo bound, and the right side is going to be the right side of the Holevo bound. Okay? So by rewriting those sides, you will see that this is Holevo's bound. So let's start with the right-hand side. So, and therefore we use the definition of the mutual information. So we start with S of PQ equal S of P plus S of Q minus joint entropy S of PQ. And in order to get expressions for those, what we have to do is we have to take this density operator in 3166 and trace out all these respective systems such that we get the density operator of P, the density operator of Q, and the density operator of the system PQ. Okay? So this is what we're going to do now. Okay, so this we can easily calculate. So we have rho, first let's calculate rho of P and Q. So we have to trace out the subsystem M. Okay, this is easy to trace out. So this is given a sum over X, Px, and then the Xx tensor rho X. And then we get rho P by tracing out Q, which is then sum over X, Px, Xx, and the system Q, I'm going to write it here, rho Q. If we take this one and trace out P, so here we get sum over X, Px, and then rho X, which is simply rho. Okay. And given these states, we now calculate the respective von Neumann entropies and plug in this equation. So first, we calculate the von Neumann entropy of, say, rho P. And from this, we find the entropies. First, S of P. So we take this density operator Now we note that those states X are mutually orthogonal. So it's simply given by the Shannon entropy of this probabilities Px, which is the Shannon entropy of this random variable X, right? And now we calculate the von Neumann entropy of this subsystem Q. So we take this density operator, and this is then the von Neumann entropy of a row. Okay? So it's S of a row. And then the last step, the von Neumann entropy of P and Q. It's the von Neumann entropy of the sum over X, Px, and then X, X, tensor rho X. Okay, and what we see here is that these operators here, they are mutually orthogonal by the fact that those X are mutually orthogonal, right? So in the sense that those combined operators X and rho X are mutually orthogonal for different X by the fact that those ones are, that X are mutually orthogonal. And for this case, we stated a theorem at some point. Let me take a look. It was theorem 3.15 and item 5. So now using item 5 of theorem 3.15, which says that S of sum over X, Px rho X is equal to H of X plus sum over X, Px S of rho X, given that rho X are orthogonal. So it's just as a reminder. And you see the structure here. Now what is here rho X is here given by those cat X tensor rho X, right? But those are orthogonal for different X. So we can use this quantity here, and what we get is now H of X plus sum over X, Px, and then the von Neumann entropy of this operator's X tensor rho X. And now we use that for tensor products, the von Neumann entropy is simply the sum of the individual von Neumann entropies plus S of rho X. And now we use that the von Neumann entropy of pure states is 0. So this is H of X plus sum over X, Px, S of rho X. Okay? And now we plug in here. So with this we find that the mutual information of P and Q. So let's plug this in, S of P plus S of Q minus this minus this. So we see that the H of X cancels, and what remains is S of rho minus this one here. So it's S of rho minus sum over X, Px, S of rho X, which coincides with the right-hand side of the Holevo bound. So next, what we consider is now here the left-hand side, right? And we continue similarly as before. So by taking a look at the state. So first we use the definition, take a look at the state, trace out all these subsystems, and then find the respective von Neumann entropies. So for the left-hand side, in 3170, we have the following, namely that S of P prime M prime is equal S of P prime plus S of M prime minus S of P prime M prime. So let's calculate rho P prime M prime. So we take the state and we trace out the measurement subsystem. The quantum system. Then we get sum over x, y, and px, x, x. Okay, let me write this here. We have trace of e, y, rho x, and then x, x, tensor y, y. Okay, so this is what we get if we trace out the quantum system. Now, what's this here? This is the probability to get the outcome y given the state x. So it's a conditional probability. Okay, so the probability to get y conditioned that we have found x. And now you see we have the probability of x times the probability of y to get a condition on x. What is this? This is simply the joint probability. P of xy. Okay. Then let's now calculate rho of P prime. So we get rho of P prime if we trace out both Q prime and M prime. So we get let's do this. So then we have sum over x, y, p of x, y times x, x. So we now took this one and also traced out this measurement subsystem. Well, now we can perform the sum over y, right, and get simply the probability to get x, right? Because it's the joint probability of x and y. However, if we sum over all y, we simply get the probability of x. And then for rho of m prime is left, take again the state and now trace out the first system p. Then we get sum over y, py. With this we can now again calculate the respective von Neumann entropies. actually pretty easy to calculate, given that we have always orthogonal states here, and meaning that from this one here, we directly get that S of P prime M prime is equal to H of, so to the joint entropy, right? Because we have these joint probabilities here, and those are orthogonal states. And then from here, we get that S of P prime is equal to the Shannon entropy of this random variable x. And from this one, we get that S of M prime is the Shannon entropy of y. Right. And now we can plug in here in this definition of the initial information of P prime and M prime. So with this, we get that S of P prime M prime is equal to H of x plus H of y minus the joint entropy. And this is simply the definition of the mutual information of x and y. Okay. So we're not finished yet. So now we found that that this expression here gives us the mutual information, and we found that this is valid independently on the exact measurement. Right? So since this is valid, independently on the exact POVM, we can choose the POVM which maximizes this mutual information such that S of P prime M prime is equal to the maximum over all POVMs of this mutual information, which is equal to the accessible information and which coincides with the left-hand side of the Holevo bound. And this then finishes the proof. Okay, so we finished now our proof of the Holevo bound, since we have seen both sides can be represented as shown in this statement of the theorem. Okay, now let me also give some remarks on this Holevo bound. So, first of all, it's in the theorem of the Holevo bound is, in quantum information, indeed an important theorem, because it gives us access to a quantity which bounds our accessible information. Right? As I told you before, in general, it's not easy to perform such a maximization over PUVMs. And with this Holevo bound, we found now a nice expression with which we can at least say that we have no more than this, that the accessible information can be no more than this upper bound. And since the Holevo bound is important, this right-hand side of the Holevo bound has its own name, and it's often called either the Holevo psi quantity or the Holevo information. So the right-hand side is the first remark. The right-hand side of the Holevo bound, which was in 3.169, is often denoted, so it's often denoted chi of E, which is the right-hand side, which was the following expression. And it's called the Holevo chi quantity. Or Holevo information. Okay, the next thing is that we now okay, Holevo bound is not written here. The next thing what we do is we use from 3. Okay, let's take a look. Okay, we use the entropy of a mixture. I stated it in the beginning of the lecture. So next, we use that the entropy of this ensemble, which is simply S of rho, is smaller or equal to h of x plus sum over x px s of rho x. So which we wrote down in equation 3.147, such that by plugging this in the equation from the from the Holevo bound theorem was 140 and 3.165. Find the following, that the accessible information, so we had that is by the Holevo bound, it's bounded by S of rho minus sum over x px s of rho x, right? This was the Holevo bound, and now we plug in this here, and then we find that this is smaller or equal to h of x, right? And this is what we stated when we motivated the accessible information. So remember that in the beginning we considered this communication protocol between Alice and Bob, and said that if Bob performs this measurement, which we can associate with this random variable y, then his information that he can learn about this random variable x is given by the mutual information of x and y. And then we stated that this mutual information is bounded by the chain entropy of the random variable x, right? And if his mutual information that Bob, if this mutual information between x and y is equal to h of x, then Bob has full information about the random variable x, right? And this is what we get now here, that the accessible information is always bounded by the full information, right? So now let me say a few words to this, under which condition we have equality here. For this we have to remember under which condition we have an equality here in 147. And in 147, if you remember or take a look, there the equality saturates if and only if we have mutually orthogonal states. Okay? And this means that this equality also saturates if and only if we have mutually orthogonal states. And then it's clear, because we know that in the case of mutually orthogonal states, Bob can learn all the information about this random variable x, meaning then we have the equality here. So let's write this down, since the inequality in 147 saturates if and only if the states rho x are mutually orthogonal. We see that the accessible information is smaller than h of x for non-orthogonal states. So this is the same as we've seen before. Now we already quantified it, that if I have non-orthogonal states, I don't have access to all the information about this random variable x. And then the last statement for today is, okay, after a moment of thought, we see that the Holevo bound implies that n qubits cannot be used to transmit more than n bits of classical information. Okay? If you think about the statement for a while, then it gets clear. So after a moment of thought, we see that the Holevo bound implies that n qubits cannot be used to transmit more than n bits of classical information. Okay, this is a really nice statement. And with this, I'd like to finish for today. and I'll see you next time. And next time we possibly do one example about the Holevo bound, and then we start with a brief introduction to entanglement theory. Okay, thanks for today.